Okay. You have another formal lab to do a week from tomorrow. Today is Tuesday, the 21st of March. I want to give you some insight, perhaps, into what you're doing in the lab. Yes, you should know what you're doing. You're testing RC circuits, obviously. But I think we introduced you to some new material as far as the frequency response, what we would actually call a Bode plot. That's to say a plot of decibel magnitude versus logarithmic frequency. I want you to know where some of that comes from, and I think some of that understanding will help clarify for you what it is that you actually did in the lab. So this is not intended to be a primer on, oh, hey, here's how to write your lab. You are supposed to write up your own labs. Yes, you can use this information to assist you in understanding what you did, but it's still got to come from you. And by the way, we do have labs from last semester, lots of them on file. So don't go using one of last semester's labs. Make your own lab up. We got them all available on Turnitin. It's real fast check. So do your own work. Anyways, let's talk about what you did. You looked at RC circuits, okay? You had an input signal, a voltage here, all right? And you drove a resistor and a capacitor, okay? And then we measured the output voltage over here. This was actually the in plus and minus. This was the out plus and minus as well. You might say, but wait, where are all the op amps? Well, this is the heart of what you were doing. The op amps were utilized so that you wouldn't load your function generator by trying to push too much current through the RC circuit. And in addition, if you directly measure the output of voltage here, that might load the capacitor. You would have had a different measurement there. And so, again, you actually used a load follower to provide this voltage from the function generator. And over here, you did have a load follower that you were measuring this output voltage with. But the heart of it all is still an RC circuit like this. So let's take a look at the RC circuit, see what's going on. We have a resistor up here, we have current going through here, and actually the current's going to wrap around like that. We use Kirchhoff's voltage law. We say, hey, look, if you look at this whole loop, we've got current going all the way through. We sum the voltages here. And so Kirchhoff's, like I said, voltage law says Vn minus I times R. That's the voltage drop over that resistor. Minus V sub C is equal to 0. And what we're saying here is that V out is V sub C, call it V sub C, call it V out, whatever you want to do. It's the voltage over the capacitor. So, what else do we have going on here? Well, we also know that for a capacitor, C dVc dt is equal to I. And if you want to, you can call that I sub C. This is, again, Kirchhoff's current law now actually coming into play. That's, again, Kirchhoff's. But we have resistance current going through there, but of course, whatever comes in here is going to go out down there, and you can call that I sub C. Or maybe we should just call them both I. It doesn't really matter. And I really would like it if you would become comfortable understanding those differences between, say, I sub C, or maybe understanding that they're all the same. So let's move on with things. The point here is this resistance, we could call it I sub C if we wanted to. We really could replace that whole term, though, with a C dVc dt. What would be the benefit of that? The benefit of that is we get a regular, ordinary differential equation. We have the equation, and I'm going to go ahead and erase my RC circuit here, because it really doesn't matter that much anymore. We get then that Vn minus, we have R times that I sub C, so in other words, RC dVc dt is equal to, or minus V sub C is equal to 0. So if we want to cast this as a regular old ordinary differential equation, usually what we would end up doing is the dVc dt. We're going to divide everything by RC. So we end up with plus 1 over RC times V sub C is equal to 1 over RC Vn. That's the differential equation you end up with. Just got to check my computer to see that it's actually pointed. Yep, it's going at the right place. Get a little bit of a glow from the lights, but that's okay. So now we have the question, what kind of response do we get? Now, if we used initial conditions on this, or if we really cared about initial conditions, then we have to consider some of the free response of the system. Free response would be homogeneous solution, it's not totally free, I guess, but it's a homogeneous solution. We might say that, call it VH was equal to K e to minus R, little RT. When we figure out what little r is and so on and so forth, it would actually be 1 over RC. But we don't really care about that in this context. Right now we're looking at, hey, what happens at steady state? So I want to know way down the road, after I apply a whole bunch of sinusoidal signals. I'm not concerned with what happens down here at time t is equal to 0, but way down there, what's it look like? So that means I'm really only concerned with a particular solution. So if we take a look at it from that perspective, then we can say, if I say that let's suppose that Vn is equal to some amplitude A, sine of omega t. And now it should start to look a little bit like the lab as well, not just the fact that it's RC. But you did apply an input voltage, an amplitude, and it was varying at some frequency omega, and actually varied at a variety of frequencies. You set it at one frequency, and you got a response. You hit another frequency, you got a response. You went through a whole bunch of those frequencies. So if this is the input, we would expect that our output is going to be something a lot like the input. And so a good choice for a particular solution, which is really to say the capacitor voltage at steady state, what does it look like? A good choice might be V sine of omega t. And the analogy that I typically make, and you may have heard me in class, is always, if I'm bouncing up and down at 1 hertz in the back of a pickup truck, then I expect the pickup truck is likewise bouncing up and down at 1 hertz. However, if we go ahead and take this, we take the derivative of this and we plug it into this equation up above for the VC here and the VC there and the user VN. On the right hand side we'll have a sine. Here we'll have a sine, but here we'll have a cosine. You can't have it so that a cosine plus a sine is equal to only a sine. You gotta have some of each. So what we do to compensate for that is we actually go ahead and say, let's go ahead and put in something, let's call it d cosine of omega t. I said compensate for it. I guess that's not a right way to put it. It's the way we would deal with it. Now, if I do that, and now I take the derivative, dv dt, the derivative of a particular solution, is going to be equal to, well, it's pretty obviously d omega cosine of omega t minus d omega sine of omega t. And so now what I do is I take this expression, I plug it in for dv dt, I take this expression, and I plug it in for v sub c, and I don't forget that I'm multiplying everything by 1 over RC. And for that matter, I take this expression, the input voltage, and I plug it in there, and again, I don't forget that I have a 1 over RC. So if I do that, then what do I get? Well, I've got a b omega cosine of omega t minus d omega sine of omega t. Like this first, I've taken this derivative and just plug it in right there. There's no RC modifying it, nothing at all, just a plain old dv dt. We're replacing that with dp dt. So next what we want to do is go ahead and by the way, oh yeah, right here, we have the plus. So we go plus 1 over RC times this particular solution. Well, now we've got this b sine of omega t plus, and I'll do the other 1 over RC times d cosine of omega t, and all this is equal to 1 over RC times a sine of omega t plus 0 cosine of omega t. And I like to put in this plus 0. It makes it very explicit. Hey, look, there is a cosine there. It just happens to have a 0 coefficient. Because now what I'm going to do is I'm going to group my cosine terms together on the left. I'm going to group my sine terms together on the left, and I'll equate the sines and the cosines. So to do that, then again I can go ahead and let's see. I got this b omega plus 1 over RC times d. We got that part. B omega plus 1 over RC times d is equal to 0. I'm taking shortcuts here, but I got some liberty to do that. You can always get caught and prove this to yourself. I'm equating this cosine term plus this cosine term is equal to that cosine term, and I divide everybody by cosine of omega t. Divide both sides by cosine of omega t, and boom, it's gone. Now I equate my sine terms. I have 1 over RC times b. Okay, okay, minus d omega. That's all times sine of omega t is equal to 1 over RC times a sine of omega t. So in other words, that's equal to a over RC. Okay, so this is my cosine equation, this is my sine equation, but again, I divide both sides by, in this case, cosine, in this case, sine, that just disappears. So now we've got two equations and two unknowns. You might look at it and think, oh, a lot more than just two unknowns. Well, I don't really. R was fixed. You grabbed that out of the drawer, you plugged it into the system, well, maybe you had it at your breadboard, but it was there, it's fixed. Capacitance, that was also fixed. Omega, that's when you, I would say, turn the dial on a function generator, except in your case, you're typing it in. But that's the frequency of excitation. A is known. That's the amplitude, how big that sine wave was, from 0 to the maximum, or half of the peak to peak, if you will. So the only things that are unknown in these two equations are the D and the B. Top equation, we can go ahead and work that out. We can actually say that D is equal to a negative d omega RC. All I'm doing is saying, let's put this on the other side of the equation and then multiply both sides by RC and then divide by negative 1. So D is equal to negative d omega RC. Plug that in here, and I get 1 over RC times B plus, because I have a negative of a negative there, okay, I have d omega squared RC, not squared yet, okay, just plain old RC, that is equal to A over RC. And being someone who's not terribly fond of fractions, I'm going to multiply both sides by an RC. And what I'll get out of that then, run out of room here, I really need more whiteboard, but what I'll get out of that is a D plus D times omega squared RC squared is equal to A. All right. So I can solve that for B. It's pretty straightforward. Let's do that. When we do that, then what do we have going on? Let's see, we got B times 1 plus omega squared RC quantity squared is equal to A. So B is actually equal to A divided by 1 plus omega squared times RC quantity squared. Got that down. D is equal to a negative D times omega RC. So D is equal to negative omega RC times A. That's the coefficient, omega RC times the B and the negative, of course. Divided by 1 plus omega squared RC quantity squared. There you go. So now we have a sine coefficient and we have a cosine coefficient for what happens. And this does lead us to some information about what happens at high frequencies and what happens at low frequencies. I guess I'll go ahead and take a quick look at this. Like I said, you've got all the time in the world on the video, so what this tells us is that the particular solution, VP of t or VC of t, I'm using them somewhat interchangeably, is actually equal to the amplitude A divided by 1 plus omega squared RC quantity squared sine of omega t minus omega RC over 1 plus omega squared RC quantity squared cosine of omega t. Okay, so I'm going to get rid of some of this stuff over here. Not terribly concerned with it. Now, again, this is where I'm going to take advantage of one of the things that I enjoy, which is telling you about other stuff, other insights that you might get out of this, but that truthfully might not necessarily be directly relevant to your life. Fast forward if you want, I guess, or take it off too tight to speed. At very, very low frequencies, this term is going to dominate that frequency, this term. The reason, well, it depends. I guess it depends upon omega and RC, the values there. Well, let's suppose omega goes to 0, if you will. okay, such that this term effectively goes away. What do we have over here? Well, we have the amplitude A sine of omega t divided by 1 plus omega squared RC squared, which we said this is small. So at very, very low frequencies, the output looks a lot like the input. There's no phase shift. No phase shift and very little magnitude change as well. Now at very, very high frequencies, okay, then if omega is really big, then this term is going to be larger than this term. And so what we'll have is that the response looks like a negative cosine. And I did lose an A here. That's my mistake there. There we go. A negative cosine times amplitude A. So it's a negative of A cosine omega t, but there is a catch. This denominator is now an omega squared term, which means it's going to get bigger than the numerator does, and so overall the system is going to get to be smaller like that. So the response will be very small at high frequencies. But, like I said, if you want to take a look at it, then if this is the function sine of omega t, and this is the function cosine of omega t, at high frequencies it actually becomes a negative cosine, which means we flip that. So let's try this again. Let's see, we have the sine of omega t like that, and the negative cosine means it's going to be coming out here. Should go to 0 at the same time as that is 1. Should go to 1 as this one being equal to 0. Goes to 0 as that one goes to 1. Now, the point that I'm making on this, there is no amplitude shift that I'm showing you. But I am trying to show you that there's a phase shift as we go along. Let's see, how we gotta get this. Oh, there we go. Essentially, the dashed line is shifted to the right. How much is it shifted to the right? Let's find out. If this is instead of being time, we make this angle, okay, this is 0 degrees, that's 360 degrees. That's 180 degrees. Half of 180 is 90 degrees. So at very high frequencies, the response should have a 90 degree phase shift relative to the input. The input, again, what we lost here is A sine of omega t. Or this would be the input if we want to say it's that. Now, granted, also, it will be very, very small. At very, very low frequencies, the output actually looks an awful lot like the input. There's no phase shift, and the amplitude does not change that much. So those are two little pieces of insight that I want you to pick up as we go along the way. Trying to show you how you can look at these things and sort of interpret them in those ways. Now, let's get back to the issue at hand, which is your lab. If we go through, and now we ask the question, okay, I got this B, and I got this B, and this is my overall response. This is not a very useful way of looking at it. It's a bit cumbersome. There's a better way of looking at the response, and that is a single magnitude and a single phase. We can say, we can go ahead and say, look, this is the particular solution, dP of t is equal to d sine of omega t plus d cosine of omega t. We can do that. That's what we've done here with the particular d and b. We can also say it's equal to the some magnitude m, okay, sine of omega t plus phi. And it really is. Now, I showed that already. At very high frequencies, when this second term dominates and this one doesn't, phi is negative 90 degrees. It's still a sine wave, but it's sine of omega t minus 90 degrees. And then there's a magnitude that changes as well. The magnitude is going to be smaller. As it turns out, you have to go through Euler's formulas and use that a little bit, but as it turns out, there's another way of looking at this, which is this is equal to d squared plus d squared, the square root of that, sine of omega t plus, let's just call it phi, where the phi is equal to the inverse tangent of d over b, the cosine term over the sine term, which I always find slightly interesting because sine is actually, or tangent is actually sine over cosine, But in this case, we're taking the cosine coefficient, which is the sine of phi, and dividing it by the sine coefficient, which is the cosine of phi. So effectively, we're saying d is equal to sine of phi, and d is equal to cosine of phi. But don't worry about it. You can take a look at it from this perspective. So now what we should do is take a look at this b and this d, plug them in there and see what we get. Well, let's do that. Go ahead and say b squared plus d squared. All right, so the numerators are the same. Okay, and then we're going to take the square root of it. So that means that we really could pull the outside out. I guess we don't have to do that, but what we could say is that the magnitude here is equal to, let's square the b term. That's going to be a squared. Okay, now we're going to square the d term, and this is divided by some denominator squared. Okay, that's this whole denominator right here, or this whole denominator up above. So it's that, and y'all make those braces just to, or brackets, or whatever you want to call them. Okay, so this is the b squared term. We're going to add to that the d squared term, so we have plus omega squared rc squared, like that. Omega squared rc squared. We have a squared again. And now we take the square root of everything in here. Well, we see an a squared here and an a squared there. That means there's an a that can be pulled to the outside of everything. If you wanted to, you can go ahead and say, this will be an intermediate step. We have a times a squared times 1 plus omega squared rc quantity squared, like that, divided by 1 plus omega squared rc quantity squared, and that's actually squared. Okay, check it out. That cancels out one of those. The a squared is going to go to the outside, and so the solution for the magnitude is actually equal to a times, it's not even times, it's divided by the square root of 1 plus omega squared rc quantity squared. Okay, now, what's interesting about that to me is we can rewrite our response. We can say that the particular solution, dp of t, now is equal to a times, if you will, a coefficient 1 over the square root of 1 plus omega squared rc quantity squared, sine of omega t plus phi, and phi is equal to the inverse tangent of. Well, let's take a look at that. I'm going to fill that in just a second. We got b here, and we got d. It's actually d over d. So let's get rid of our magnitude right here. So inverse tangent d over d is going to be equal to negative, well, let's see, from the inverse tangent of negative omega rc times a divided by this stuff inside the brackets all over an a divided by also everything inside the brackets. The brackets cancel out, and so it's actually equal to the inverse tangent. Oh yeah, the a's also cancel out. It's equal to the inverse tangent of a negative omega rc, like that. So I'll put that over here. Okay, so where does that take us? What do we do with that? Well, first things first, I'll take a sip of my coffee to keep my throat being dry. Okay. Stay with us. Get rid of some of this crud. Often, not even often, almost always, what we're interested in these types of situations is if you put in this much input, how much output are you going to get? So we assume something called linearity. We assume that if you put in 2 of something that you're going to, or if you put in something, you get something else out. You put in 2 of something, you'll get 2 somethings out. Stuff like that. It's not very Dr. Seuss or study. The point is, we put in some amplitude of A, sine of omega t, and we get out A times this coefficient here, square root of 1 over, square root of 1 over the square root of 1 plus omega squared times the RC quantity squared. So really what we're doing is we're saying we would get out A at some frequencies, but we're going to multiply it by this weighting factor, if you will, that varies as omega varies. We change, as the frequency changes, this factor changes. And it's very, I mean, if you look at it right now, we talked about R is known, C is known, A is known. Omega is the one that we're varying, okay? We're changing that frequency as we move up and up and up. And so what we're seeing is that as omega gets to be bigger, the overall response gets to be smaller. Or another way to look at it is, okay, this term gets to be smaller, 1 over an ever increasing number down below. So the coefficient gets to be smaller. What I get around to is, if we wanted to ask the question, what's the ratio of the output amplitude to the input amplitude? Well, the output amplitude is this. And the input amplitude is simply A. We call this the magnitude ratio, or the transfer function magnitude, maybe would be another way, or maybe the magnitude of the frequency response. Let's call it G for the sake of argument. It's probably a bad idea to not put like braces of absolute values around, but let's just call it G for now. G then is going to be equal to the output amplitude divided by the input amplitude. So we have A times 1 over square root of 1 plus omega squared RC quantity squared, and we divide that by A. This is the output amplitude, this is the input amplitude. Oh, what do you know? They disappear. And hence linearity, that's why we care about linearity. So the magnitude of the transfer function, we can call it, is equal to 1 over the square root of 1 plus omega squared tau squared. Where'd tau come from? Well, look, we've talked about this considerably in class. Tau is equal to RC, that is the time constant of the system. And rather than carrying around an R and a C, I'd rather go ahead and just put it as a tau. So this is the first part of what I was talking about, or what I'd like to talk about. I'm going to talk next about some of the plotting and why we do logarithmic plotting and all that. But I'm trying to get around to, we have, this is the magnitude of the frequency response. The phase, you'll notice, there is no input to output ratio of phase. The input phase is 0. We don't look at ratios, we just look at the phase itself, and that's the inverse tangent of a negative omega times tau, like that. Excuse me. So these are the two responses. This is what we would consider the frequency response of a first order system with a time constant tau. It also is particular to the situation like the RC filter, where if you put in 5 volts as an input, say you put in a step response of 5 volts, you will get 5 volts out. I'm saying that because the ratio at steady state for a constant input is 1 to 1. You put in 5 volts, you get 5 volts out at steady state for a constant input. That's not always going to be the case if you have a mass sliding on a viscous surface and you apply some force to it. You will also have first order behavior. You'll also have a first order differential equation describing it. But just because you put in 1 Newton doesn't mean that you're going to get 1 meter per second out as a velocity. You get something else out depending upon the mass of the system. So the input to output ratio at very, very low frequencies for the RC circuit happens to go to 1. It's 1 over the square root of 1 because the omega gets to be 0. That's a special case, but it's really pretty cool for this. It shows a lot of insight for this particular situation. So that's what I'm talking about as far as deriving the magnitude and the phase. Now the question is, what do we do with it? I'm going to pause this video and then get back to that.